Today we are going to learn from the chapter Structure of the Atom. After the discovery of subatomic particles like proton and electron, different atomic models were suggested by different scientists, like Thomson's model of atom, Rutherford's nuclear model of atom, Bohrs model of atom. So today we are going to learn about these atomic model. First of all, I will take up Thomson's model of atom. When it was well established that atom contains negatively charged particles and positively charged particles within the atom, the question arises how these negative and positive charges are distributed within the atom. Therefore, J.J. Thomson in 1904 proposed atomic model where he tried to explain that an atom was a sphere of positive charges in which were embedded number of electrons sufficient to neutralize the positive charge. This may also be compared with a watermelon in which seeds are like electrons embedded in the red area of the watermelon, which represents the positive sphere. This model of atom is called Thomson's model of atom. Rutherford's model of atom. After Thomson's model of atom, Rutherford in 1911 performed certain experiments in which he bombarded a thin foil of heavy metal like gold with a beam of fast-moving alpha particles which were positively charged particles, and he tried to explain his observations to give his model of atom. The main observations he made were most of the alpha particles passed through the foil without undergoing any deflection. Next, some particles were deflected through small angles and a few were deflected through large angles. Very few alpha particles were deflected back. He tried to explain his observations. Since most of the alpha particles passed through the foil without undergoing any deflection, there must be sufficient empty space within the atom. Since some alpha particles were deflected through small angle or a few through large angle, and alpha particles are positively charged particles, these could be deflected only by some positively charged body present within the atom. Since some alpha particles were deflected back and alpha particles are heavy particles, these could be deflected back only when they strike heavier body inside the atom. Since number of alpha particles deflected back is very, very small, this shows that the heavy body present in the atom must be occupying a very, very small volume. The main points of his model are: an atom consists of two parts, nucleus, extranuclear part. The entire mass of the atom is concentrated in the nucleus. To explain that the electrons do not fall into the nucleus as a result of force of attraction, Rutherford suggested that electrons are not stationary but were revolving around the nucleus in certain circular orbits. As a result, centrifugal force comes into play, which balances the force of attraction. Thus, this model is similar to our solar system, where the nucleus is like the sun and the electrons are like the planets. But despite all these valuable observations and conclusion, there was one drawback of Rutherford's model of atom which he was unable to explain. Rutherford's model could not explain the stability of the atom. This is because, according to Rutherford's model, an atom consists of a small, heavy, positively charged nucleus in the center, and the electrons were revolving around it. Whenever a charged particle like electron is revolving around a central force, like that of a nucleus, it loses energy continuously in the form of radiations. Therefore, the orbit of the revolving electron will keep on becoming smaller and smaller. In other words, the atom should collapse. But this actually does not happen, and the atom is quite stable. This was not explained by Rutherford. Bohr's model of atom. To explain the stability of atom, Niels Bohr, a Dutch scientist, presented his model of atom. The main points of his model of atom are: an atom consists of a small, heavy, positively charged nucleus in the center, and the electrons revolve around it in circular paths and orbits. In a particular atom, the orbits in which the electrons revolve are the distinct orbits having fixed energy. These distinct orbits are therefore called energy levels or shells, and these are numbered as 1, 2, 3, 4, or named by letters K, L, M, N. The energy of these shells increase as we move outwards from the nucleus. But the gaps between the successive energy shells decrease as we move outwards from the nucleus. So, as long as an electron is revolving in a particular orbit, it can neither lose energy nor gain energy. Thus, the atom is stable and does not collapse. Energy is lost or gained by an electron only when it jumps from one orbit to the other. So, according to Bohr's model, as electrons cannot radiate energy while revolving in different orbits, therefore, it explains the stability of the atom. And therefore, the drawback of Rutherford's model of atom is taken care of by Bohr's model of atom. Thank you. Today we are going to take up the topic of atomic number from the chapter Structure of the Atom. Atomic number of an element is equal to the number of protons present in the nucleus of the atom of that element. For example, nucleus of hydrogen atom contains only one proton, so its atomic number is 1. Nucleus of carbon atom contains 6 protons. Therefore, its atomic number will be considered as 6. Nucleus of chlorine atom contains 17 protons. Therefore, its atomic number will be 17, and so on. Since a normal atom as a whole is electrically neutral, and each proton carries 1 unit positive charge and each electron carries 1 unit negative charge, therefore, number of protons present in the nucleus must be equal to the number of electrons present in the extranuclear part. Therefore, we say atomic number of an element is equal to number of protons in the nucleus is equal to number of electrons in the extranuclear part. It is important to remember that the number of electrons is equal to the number of protons only in the neutral atom. In case of ions, the number of electrons may be less or more than the number of protons. Therefore, atomic number should always be calculated from number of protons in the nucleus. Some important characteristics of atomic number. Atomic number is always a whole number. This is because an atom always contains whole number of protons, not in fractions. All atoms of the same element have same number of protons in the nucleus and hence have same atomic number. No two elements have the same atomic number. For example, atomic number of carbon is 6. No other element can have atomic number equal to 6. This means atomic number is the characteristic property of an element. In fact, I would say it is the identity of an element. Each element has fixed value of atomic number. Atomic number of an element does not change during a chemical reaction. This is because during a chemical reaction, there is only rearrangement of electrons between atoms. Atomic number of an element is usually denoted by the symbol Z, and it is written as is shown here. The symbol is written of the element, and on the lower left hand side is written the atomic number. Now we are taking up the topic of isotopes from the chapter Structure of the Atom. Isotopes are the atoms of the same element which have same atomic number but different mass number. As atomic number of the element is equal to the number of protons in the nucleus or number of electrons in the extranuclear part in case of neutral atom, this implies that they contain the same number of protons as well as electrons. As mass number is the sum of protons and neutrons, but protons in them are equal, the difference in mass number implies that they contain different number of neutrons. Therefore, we can say isotopes of an element differ only in the number of neutrons present in the nucleus. For example, hydrogen. There are 3 isotopes of hydrogen represented as shown in the figure here. These are called as protium, deuterium, and tritium, as each of them has atomic number 1. Each of them contains 1 proton in the nucleus. However, as the number of neutrons is equal to mass number minus atomic number, they differ in the number of neutrons. Protium has 0 neutron, deuterium has 1 neutron, and tritium has 2 neutrons. General characteristics of isotopes. Isotopes have same atomic number. The isotopes of an element have same atomic number, and therefore have same number of protons in the nucleus and same number of electrons in the extranuclear part. Isotopes have different mass numbers. The isotopes of an element have different mass numbers and they differ in the number of neutrons present in the nucleus. Since isotopes of an element have same number of electrons, they have same electronic configuration and hence the same number of valence electrons. Since chemical properties depend upon the number of valence electrons, therefore isotopes have same chemical properties. Different physical properties. Since the isotopes of an element have different masses, they have different physical properties like melting point, boiling point, density, etc. Also, isotopes have different nuclear properties. Applications of isotopes. Isotopes are used in the nuclear reactor. For example, isotope of uranium U-235 is used as a nuclear fuel. Isotopes are used in medical field. Some radioisotopes are used for treatment as well as diagnosis of fatal diseases like cancer, tumor, etc. Like cobalt with mass number 60, which we call generally cobalt-60 isotope, is used in the treatment of cancer. Phosphorus-32 isotope is used in the treatment of blood cancer. Iodine-131 isotope is used in the diagnosis and treatment of thyroid disorders. Isotopes are also used in carbon dating and for various purposes in industry. Thank you. Just as isotopes are atoms of same element with same atomic number but different mass numbers, we have atoms of different elements which have different atomic numbers but same mass number. Such atoms of different elements which have different atomic numbers but same mass numbers are called isobars. As they have different atomic number, they contain different number of protons as well as electrons. For example, atomic number of argon is 18, while the atomic number of calcium is 20. Their atoms are known which have mass number 40. Thus, we may represent them as shown in the figure here. Number of protons is shown in argon. Number of protons is 18, electrons is 18, and number of neutron present is 22. In the atom of calcium, atomic number is 20, its mass number is 40, proton present is 20, electrons present is 20, and number of neutrons present is also 20. So argon and calcium are examples of isobars as they have same mass number but different atomic number. Some important characteristics of isobars. Isobars are atoms of different elements. They have different atomic number. They have same mass number. They possess different physical and chemical properties. They have different number of protons, electrons, and neutrons. Hope the difference between isotopes and isobars isobar is clear to all of you.